Hello, welcome to this session about advanced dimensional modeling in Power BI. What are we going to cover the coming 45 minutes? Let's take a look. We're going to do a short introduction about vector dimensions, star schemas, look into relational tables and models, how to generate dimensional models out of that, how to work with many-to-many relationships and how to compare different fact tables with each other, how to use the date table, how to look into cross-filter directions. So what is the direction of the filter and when do you set it to both, for example. How to handle master detail tables. Sometimes you don't want to merge these two tables into one, like invoice and invoice lines, but want to keep the table separate. So we'll cover these scenarios. We're going to look at inactive relationships, like for example role-playing dimensions. Like the date table, it's connected to the order date and the ship date, and how to switch between them. We're going to look into slowly changing dimensions, looking at import versus direct query. How does that affect your model, and working with aggregation tables. And we're going to look into the Vertipaq engine. Who am I? My name is Arthur Kraus, Power BI and Fabric trainer, consultant, developer. I give a lot of trainings about Power BI and Fabric, but also do a lot of consultancy work. And I recently started a new website, fabriccode.com, where you can find a lot of scripts, Doc scripts, M scripts, Python scripts, if you want to do some more advanced things in Power BI and Fabric. Okay, let's get started and let's dive right into it. We have the concept of a data warehouse. I think it's familiar for everybody. We import data from the source systems in there every night. We have a lot of tables, hundreds, even thousands of tables. And we could create all our reporting on top of that. But it's not really that easy to do because we have a lot of tables, a lot of relationships, technical tables. It's difficult to create reports from that. Especially if you're not a diehard SQL person, like a business person. You can never create reports on top of these databases. So that's why we create data marts. And in these data marts, we have the star schemas with the vector and dimensions. And that's the same what you do in Power BI. We create like mini data marts on our semantic model. And let's take a closer look into that. So if you create a semantic model in Power BI, we normally use vector and dimension tables. The fact tables are the tables with the numbers that you want to aggregate, that you want to summarize. That's what you see in the chart on the y-axis. Or for example, in a pivot table, these are the values. And the dimensions is where you want to break it down by. I want to see per month, per product category, per action, per customer, per country. I want to see the total sales. So dimensions are always used for filtering and grouping. And then normally on the one side. So we have unique list of products, unique list of dates, unique list of customers, unique list of stores. Everything is unique. And it has a primary key, which is connected to a foreign key in the fact table. So this is how it normally works, and this is the best practice to work in Power BI, create a fact table and then dimension tables. But what if you have multiple fact tables? That's like a more advanced scenario. So let's start there. First, I'm going to look into a relational database, because normally the data is not in the fact and dimension format. Maybe the data platform guys, they created like a data mart with fact and dimensions, but a lot of times you don't have them. So you have to model it yourself. And here I have, for example, a table with customers. Every customer has a unique ID, and that's a dimension table. And then we have for each customer a lot of orders. So that's a fact table. I can count the number of orders. It also has the date column, order date. And this order table also has lines. These are also facts, because there you can see the quantities that are being sold and the pricing. So these are both fact tables. The products table, on the other hand, is a dimension table. I want to group on it, filter on it. And the category is also a dimension table. What we normally want to do is to keep it simple. So I'm going to merge the products and the product categories tables into one dimension table products. Makes sense. I don't want to snowflake things. If we have extra dimension tables, that's what I call snowflaking. And I want to keep it as simple as possible. And here, these two tables, we normally also merge them together. Why? Because then we just have one fact table and we don't have any problems with the filter direction, because this relationship will have a filter direction, cross filter direction, pointing from one to many, which means that I cannot filter the other way around. So if I filter on a product name, I will see the order lines for that product, but it will not filter out the orders and the customers that bought this product. And that gives all kind of problems. So that's why we do normally create a star schema like this. We have the orders table in the middle, the fact table, and the products and customers as dimension tables. Okay, but what if we have multiple fact tables? How can we combine them? Then it becomes a little bit more advanced. Say, for example, I have another fact table that has the targets. So the orders table is like these are the actuals, what kind of sales did we have. But this is the target, this is what we want to have. I want per month, per subcategory, a revenue of, in this case, from January 2022, for helmets, I want to have a revenue of 10,000 euros, for example. And then I need to have like a relationship. But the problem is that this is one many to many. So we have a products table, but we have a lot of products with the same subcategory. And we have also a lot of targets for the same subcategory. So I cannot just drag this column because it's many to many. So there's some rules to that. There's nothing wrong with many to many relationships when you use them the correct way. So in this case, what I can do, I can create a relationship from subcategory to subcategory. And it's important that the filter direction is always pointing from dimension to fact. Or otherwise, Power BI will get confused. And especially with many to many, Power BI doesn't know what the filter direction should be, because it doesn't really know what the fact and dimension tables are. So that's where the filter direction comes in. You also see it's a different kind of relationship, it's less strict. This is what I call a limited relationship, or they used to be called weak relationship. That's also probably why a lot of developers didn't want to use them, because yeah, who wants to create weak relationships, right? You want to have strong relationships like this. This is a strong performance relationship, and this is a weak limited relationship. It's less performant, but it's very useful in these scenarios. So if you have small tables like this, the sales targets is normally not that big. We don't have 10 million targets, probably. You can have a lot of orders, so that can be a big table, but the targets is on a higher granularity, so it has less rows. So probably it's a good candidate for many-to-many relationships. So the performance normally is not really an issue. It's about convenience for creating reports. That's what the whole data mart and star schema was all about in the first place, right? It's not only about performance, it's about usability for creating reports. So we can create this relationship. You can just drag the column subcategory to subcategory, or category in this case, and here you can set the filter direction. And then what you can do, then you can, in the matrix, I can put the subcategories on the columns, and I can compare the line total with the target, the actual, compare it with my target. And that just works. One thing to pay attention to though is that you take the subcategory from the correct side of the relationship. If I take it from products, it works. If I take it from sales targets, it doesn't work because it has to go across the filter direction. And that's not possible. It's a one-way street. You cannot go the other way. So normally we hide these columns. So it will hide the subcategory and this side so that you can never go wrong. But what now if I want to also add the year? If I take the year from the orders table, here we also have a year column, then what you see will happen, it will filter the line totals correctly, but it will not filter the sales targets, because there's no relationship between this year and this year. Is it an idea to connect the year with the year? Let's see if that's possible. So let's go over here to my Power BI desktop. So first let me drag the subcategory onto the subcategory. Here I can set the filter direction from dimension to fact. That works. I'm gonna hide the subcategory. That's always important. And then if I go over here, I already added the subcategory for the products table, so that's the correct one. Here I'm gonna add the year, for example, from the sales targets. And as you can see, now it's gonna filter the targets, but not the line total. So yeah, it also doesn't work. So the question is, how can I connect these? I could drag year over to year, but yeah, that doesn't work. Why not? Because these are two fact tables. I cannot have a many-to-many relationship between two fact tables. Because here I have duplicate years and I also have it at this side. And now I need to choose a filter direction. So if you use many-to-many, always choose a filter direction. It's never both. That's a bad practice. And in this case, I cannot choose because these are both fact tables. There's no filter direction running from dimension to fact. So this is not allowed. So this is an illegal option. So how could we solve this problem? I think most of you already know how to solve this. A suboptimal solution would be to create a years table. That would be the dimension table for the years. And then this will be connected to the years of the orders, the sales targets and the population. What will be a better solution? And it will actually work, but you cannot drill down to the month or the quarter. A better solution would be to create a date table. I think everybody knows this already, and you probably created already in Power BI, but this is the reason why you need it. You always need to have a date table to create the connections. And you can create this date table using DAX formulas or import it from SQL Server. A lot of options there, or maybe use an M script in Power Query. It's all fine. I normally tend to use DAX functions for that. Especially the function calendar auto can generate like a date table for you with a date column, and then you can add DAX formulas for the other columns. The nice thing about doing it with DAX is that you can also use it when you're not connecting to SQL Server. Sometimes you create a report that doesn't use SQL Server data, but gets things from Excel sheets or REST APIs, or some business people want to create reports using Excel sheets. Yeah, then this works the best, because you can use it in any scenario. If you look at the completed model, then it would look like this. We have the date table that has unique dates. It's connecting to the date columns in the orders table, for example, the order date or the ship date or the invoice date. There's always normally a date column to connect to. How would you do it with the sales targets? We don't have a date column there. Of course, you can create a date column, like take the first of the month and connect that, or you can use like a many-to-many relationship again by combining the year and the month in a separate column and then create a connection on that. Because the granularity of the sales target is on the month level, so that's why I create like a concatenated year-month column and then create the relationship. Here you can see this column in action. So here I created year and month in a separate column. I use some DAX formulas for that to concatenate them. And I did the same in the dates table. There we also have year month column, year and the month. Then we have something in common, and then I can create a relationship between them. Where is it? This one. It's connecting year month to year month, and the filter direction is again from dimension dates to sales targets. And then we can create the matrix, and now I can put the year and the month from the date table on the rows. And if I choose a specific month, I can see here the actual versus the target. And here you see how you can combine two fact tables and put them in one matrix and combine the values of both, using the dimensional model with the fact and dimensions. Another important thing related to date tables is this setting. In the data load section, we have the auto date time setting. This is by default, it's checked. What does this do? Let me show you. Here I have the date table connected to the order date and the ship date. And here I have a birth date column. If you look here, the customer's birth date, it's connected to a date table, but that's not my date table, because that would have these columns. This is like a hidden date table generated by Power BI, while the date column, it doesn't have that, and all the other date columns like order date and ship date also don't have that. So only the column that is not connected to the date column of the date table, for that Power BI generates auto date time. And if you would look at it like with Doc Studio, an external tool, then you would see there would be a hidden table, local date table in this case. And if I evaluate, meaning looking at the table like this, you see it's starting at 1937 and it's ending in 2008. So this is the birth date column. I don't want this table. So how to get rid of it? Just go to the options and settings, options. Here I can uncheck it. And if I never want to see this setting again, I can also do it globally. I can also uncheck it there. Yes, now I press OK. If I go to Doc Studio again, you'll see this hidden date table is fully gone. So that's what you normally want. Now let's take a look at the next subject, cross-filter direction. What does this mean? If you have a dimension table and fact table, then the filter direction is always from one to many, from dimension to fact normally. That's default for one to many, and is also best for performance. So if you have a one-to-many relationship, it's best to leave it at single and everything just works. When would you want to use both? What scenarios? For example, if you have a one-to-one relationship, basically two tables that you could merge together, but for some reason you don't want this because these are different kind of data in there. And then the filter directions should be set to both. Another reason is what we also cover on the next module. If you have master detail tables like order and order lines, and you want to keep them as separate tables, then in between we should have a filter direction both. Because then from dimension tables, we can filter through these two fact tables. And for the rest, we don't want to use it because it's slow for performance. And especially if you have many-to-many relationships, you would never want to set it to both. Because then Power BI gets confused and is not how it should be. Let's take a look at a scenario where you might want to set the filter direction to both. See, here we have this model with customers, orders and products, and what I want to do, I want to calculate the number of different countries. But this country column is not in the fact table, but I still want to create a measure on top of it. As you can see here, the country is on the dimension side. And because the filter direction is the other way around, the filters that you apply to the fact table will not be applied to the customers table because the filter direction is the other way around. So how do we get around this problem? There are a few options. Let me show you. So here we have this matrix. Let's say I created this measure. I do a distinct count of customers country. If I drag it in the matrix, it will simply not work because we go against the filter direction. So this is not the solution. So what can we do? Two options. Either we're going to denormalize, so the thing that we want to calculate on, we're going to put it in the fact table because if you want to aggregate on it, then basically it is a factor. So in this case, I can take the country and put it in the orders table. I can do this using a calculated column, country equals related customers country, and then I can do a distinct count on top of that. And then it will just work. Let me show you. If I go over to the fact table orders, here I created a country column. Related customers country is going to look up this customer ID on the one side. And then here I have distinct orders country. And then if I drag it in, you see it's just going to work. What could be an alternative if I go back to this one that didn't work? So in this case, it doesn't work. But what you could also do is change the filter direction. The filter direction is now set to single. But what would happen if I set the filter direction to both? Okay. So now it's set to both. So that means that all the filters applied to the orders table will also be applied to the customers table. So now this measure that didn't work before works now. But the downside is that, yeah, now it's always filtering both ways. So even if I'm not working with the customers at all and doing nothing with it, it will still filter it always. So that comes with a performance penalty. So what you could also do is set it on in the measure. You can also change this filter direction in the measure. So for example, that's like a second option. You can also create a measure with a calculate. You say, I want to calculate the distinct count of customers country with a cross filter, bidirectional, set to both. The relationship you don't have to change, but for this measure, temporary, we're going to set it to both. And then again, it falls back to single. Now let's take a look at master detail tables. I have two scenarios for you. One is a purchase order, that's the master table. That's the header information. And then we have the purchase order lines, that's the details information. And also I have the invoices and the invoices line. One invoice has multiple invoice lines. Let's take a look at the data, how it looks like. So here we have the purchase order table. So here you have one purchase order ID with a specific date connected to a specific supplier. And then we have multiple lines for that purchase order. In this case, 2 lines for different office supplies, for example. The same with invoices. So we have invoices for that same supplier. It's also connected to a specific purchase ID, but not always. Sometimes you have an invoice without a purchase order. And it's connected to book year. And this invoice has, again, multiple lines. How can we model this? So basically we have 2 ways to model it. I could just connect these tables as is. So these are the tables so as they are in a database. I could connect them and we get more or less like a relational model. So we wouldn't end up with fact and dimension tables. But let's start off first with the dimensional approach. So we have a fact table for purchase orders and a fact table for invoices, and then the dimensions around that. How would it look like? We see the solution here, fact purchase orders with the lines and the header information combined. The same with the invoices, invoice master and the detail lines together on one table. Just like the same like we did with the orders in the previous slides. So this is a general way of working. We want to have a fact table and the dimensions as a star around it. And that kind of works. If you look at the table, fact invoices, you will see the invoice information. And you see the line and the header information combined in one table. So we have some duplication. The date is the same, the supplier is the same, purchase order is the same, but the line information is different. And the same with the purchase orders. And I could also create some calculations on top of that. For example, if I want to calculate the total purchase order line total, I could do a sum of the line total. I can summarize the invoices, the line total, and I could visualize it like this. So here I can choose, for example, department IT. I see here are some suppliers. I see the total invoiced amount and the total purchase order amount. You see in this case, it's the same. But for example, this purchase order, there were not any invoices yet for this period. So this works all fine, but what are some problems you may encounter when you choose this version of the model? And what if you want to calculate or filter on the master level? So for example, what I want to do is I want to count the number of purchase orders with a total amount of all the lines greater or equal to 1,000 euros in this case. That's a little tricky to do because if I look at the table and if I go to purchase orders, where would I filter on? I need to sum them first. 2022-07, that is above 1,000 euros, but the lines themselves are below. So I cannot just filter on the line total. First I need to aggregate it, summarize it, and then I want to do the filtering. And then you get difficult DAX formulas. So yes, it's possible, but it's not that easy. What you could do is you could here go to the fact purchase orders and add like a purchase order total and summarize this. Then you would have like 420 here and here these two combined. But then you would have a lot of duplicate values. And if you do by accident a sum of it, you get too high values. So that's also not really what you want. So maybe in this case, if you really need this header information, then you can also look at another solution. And that's it. It's that you more or less have like a relational model. So it's like the database. So we keep the purchase order and the purchase order lines as separate tables. The same with the invoices. And what then we can do is we can add an extra column, like a calculated column, or we can do it with SQL to calculate the total amount of all the lines together. And on that column, we can put filters, if you will. So these are the tables and the relationships. So it's connected via the purchase order ID, and here it's connected on the invoice ID. If we look at the purchase orders table, you see I added a total amount, and the total amount, it's going to get the related lines, and it's going to summarize all the line totals to get like the grand total on the master level. And then what you can do is you can create this measure pretty easy. I want to calculate the number of purchase order, which is the count of the purchase order already, where the total amount of the purchase order is greater than or equal to 1000 if you like. And this makes all a lot easier. And I can still create all the calculations that I want without any problems. In the next module, we'll look at some extra things that you might do here. For example, this relationship, it's now one directional, pointing from one to many, but you would see in real life, you would make it cross-filter direction both. I'll show you that. And also this purchase order ID, of course, I want to also connect it to this purchase order ID. For that scenario, we're going to use inactive relationship. Let's take a look. So here I have a department and some suppliers. I have a purchase order total of 2,800. And I want to see how many percentage of that is already being invoiced. So I want to have a drill through, and I want to see the purchase order total, and the invoiced amount. So I can also calculate a percentage. But by default, this is not possible because there's no connection between the purchase order and the invoice order. So what we need to do as a solution is to create this connection between the purchase order header and the invoice header, but it should be an inactive relationship. Why is that? Because if I create it as an active relationship, then it will always, the purchase order will always filter the invoices. So sometimes you have invoices that are not connected to a purchase order, and these will not be shown then in the report. So the numbers will not be correct. So I want to be able to activate it whenever I need it. So if I go to the drill through page, then I want to activate it. And this can be done using the function use relationship. You can activate the relationship at will using a specific measure. So let's take a look how it works in the demo. So here you have the saturation, it's not working. So it's not being filtered. That's the normal measure. So now I'm going to use this one. Invoice line total for a specific purchase order. So I'm going to use the calculate with the use relationship. What does the use relationship expect? It expects two columns, column 1 and column 2. They should be connected with the relationship. If they're not connected, you get an error message because first I need to create the relationship. So I connect purchase order ID with purchase order ID. I disable the relationship like this. And then I can switch out this measure and change it with this one. And now it just works. So now you can see how much amount is being invoiced for that specific purchase order. Let's take a look at another problem that we need to fix in this model. If I go back to totals per supplier, what if I want to calculate on the master level? For example, I want to see the number of invoices that the supplier sent. Then you see the numbers are off. So this number of invoices is being filtered by the supplier, but is not being filtered by the department. Let's see what's going wrong. It has to do with the filter direction. So the invoices filter the invoice lines. Also the supplier filters the invoice lines. The cost center, the departments filter the invoice lines, but they don't filter the invoices. That's why you see the higher numbers here. So what's the solution? We need to set the filter direction of this relationship to both. Because the invoices and the invoice lines are both kind of fact tables. So we want to be able to filter through these two fact tables from the dimension tables to the fact tables. That's the downside of having master detail tables in the middle. These are both fact tables, so they should always have the filter direction set to both. And then it just works. Let me show you. So this filter direction should be both, like this. And then the numbers are correct. Another common scenario where you will find the use relationship is with role-playing dimensions. For example, this date table is connected to the orders table, the fact table, to multiple columns. So the default relationship is date connected to order date, but I also want to connect the date to the ship date, or the invoice date, or the start date, or the end date. And I want to be able to count the orders that are being sold on this order date, but also the orders that are being shipped on the ship date. So for that, I can use the use relationship. I'm going to calculate the number of orders, but then using the ship date. So that works perfectly fine. And then you can combine these two measures in one chart or a matrix and see the numbers. So that's all fine. But what if you want to drill through and also see the orders that are being shipped on that specific date, for example? So we want to be able to drill through and see the orders ordered on the 7th of May and the orders shipped on the 7th of May. Let's take a look how to do this. So I added two drill through pages, one for the orders connected to the number of orders shipped connected to the order shipped. What happens if I do a drill through, for example, here on this, let's start with the orders. These are 8 orders. I want to drill through to the orders and I see these 8 orders. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so that works. And now I want to see these two. The orders are being shipped. Let's take a look. And I don't see the two. I see still the same orders that are ordered on the 28th of May. Because this is the default relationship. That is what's going to use by default. So how to solve this? Simple hack. Just add the measure to the table. So for example, number of orders shipped. I'm going to add it. And then it's going to filter it automatically. So now it knows you want to look at it from that perspective. And now you're going to see these two orders being shipped on the 28th of May. Next topic, we're going to look into slowly changing dimensions. This is normally something that data engineers worry about in a data warehouse or a data lake to capture changes on the dimension side. Say for example, a customer moves from Los Angeles to New York, and then you need to track when did the customer live in New York and when did he live in Los Angeles. So if you filter on, for example, Los Angeles, then you want to have the facts for that customer living in that area in that moment in time. So how do we do this? So there are basically 3 types, slowly changing dimension types 0, 1 and 2. 0 means you do nothing. So if something updates, then you just ignore it. That's normally, of course, a bad idea. So we also have type 1. That's what you normally do in Power BI. If something changes in the source, you get a new download and you just import it in Power BI and you overwrite the existing value. So you just update, for example, the address of a customer and you don't know what the previous address was. This is if you work with downloads from systems, you just download the data, you import it and the rest is gone. Hopefully, if you connect to a database, a data warehouse, that they manage this and they track all the changes. And a lot of time in a data warehouse that is tracked, but in the source system you get the data from, it's not always captured. So you just lost the information. So how can we solve this? What we do in a data warehouse, we have slowly changing dimensions type 2. So every time something changes in, for example, a supplier record, we create a new record. And in this new record, we have to change. So for example, here, this supplier moves from California to Illinois. And here we close down this record. And then we open a new record that's active from the 22nd of December. And then we get also a new supplier key. This is what we call the surrogate key. It's not known in the source system. That's what's the supplier code. That's the code that you know in the source system. And this is like an increment key, an identity field in SQL Server, for example, is auto-numbering. And then we need to look up this number and then put it in the fact table so that everything is connected correctly. We cannot really do this in Power BI. We cannot do real slowly changing dimensions with the start and end date. This is really something that you need to do in the database. This is for the data engineers. But we can fake it a little bit. So what you can do in Power BI is download exports. So if you have like a list of suppliers, you can capture it every year and then have like a snapshot of the suppliers for that specific year. Or you can even do it per month if you like, if it changes quite a lot. So then you will have 12 versions of the supplier list. And how do we distinguish between them? We add also like this surrogate key. So in this case, for example, I take the supplier code and add to it the year, and with that I make it unique. And then here we can track the changes. So this is the address in 2022 and this is the address in 2023. How do we connect it then to the facts? Here on Power BI Desktop, I can show you how it works. So this is the supplier table with the unique ID. And then if I go to the purchase orders, you see we have there also this supplier ID. So let's say if I order on supplier code, you can see here in 2023, this purchase order is connected to this version of the supplier, and this purchase order is connected to this version of the supplier. And with that, we get maybe a different address. So for example, now if I add a new column, and I'm gonna look up the address just to show you that it's the same. With related, I can look it up. You can see we have the same supplier and we have different addresses tracked correctly with the facts. So next up, we're going to look at import versus direct query. Let's look into it. If you're working with SQL Server, Azure or on-premises via the gateway, you can choose if you want to import the data or you want to do direct query. Let's take a look at the differences. Import means that you import the data in the data set, and you have full support from Power Query. You can use all the Power Query bits and pieces that you like. Downside of using a lot of Power Query things is that not all the transformations that you do can be query folded into SQL. That's also the reason why direct query doesn't support all these features. Direct query, you normally have a SQL statement, you execute it, that's it. You don't do anything in Power Query. Because you're importing data, the data set is limited size-wise, because we basically have a copy of the data. In Pro, it's 1 gigabyte Pro workspaces. If you have Premium, you can go up to 10 gigabyte and even more if you enable the switch. It's also limited refresh-wise. You can refresh like 8 times a day or even 48 times a day. But normally we connect to a data warehouse, and this data warehouse is not refreshed this often. So this is really not really a problem. But if you connect to a source system and you want live data, yeah, then direct query can bring you this. It's always real time connected to the database. If you look at DAX, it used to be quite limited what you could do with direct query, but now they fixed that, so you can do basically anything. Only really advanced DAX, yeah, will get you into problems. Especially performance-wise, it is a lot slower if you have complicated DAX formulas. So what are the scenarios for direct query? Use cases, real-time operational reports, small data sets, you need this live connection, then direct query is perfect. But what if you have really big databases, like big data, and it's impossible to import terabytes of data? Then yeah, you don't want to use import, of course. Then also you can use direct query, especially for the drill through. And that scenario is what I want to show you. You can import aggregated data like per month or per day. And if you want to drill through and see the individual records, then you can use direct query to do that. So you don't need all the details in your data set. And sometimes you also have row level security in source system, like with tabular models or cubes, OLAP cubes. Then you also want to do direct query. And for all the other scenarios, always use import. Here I have a report that is set to direct query. So if you look into the model, you can see orders, products, and product categories. They're all direct query, directly connecting to the database. And if I want to see what the performance is, I can use the performance analyzer here in the view menu, performance analyzer. Let's capture it. It's tracking. So now if I choose a different year, for example, 2022, you can see, okay, now it takes quite a long time, 800 milliseconds to get the data because it's using direct query. So what I want to make it a little bit faster. What you can do is you can use aggregations for that. What do I mean by aggregations? if I go over to the tables, what I added to this model is an aggregation table. So this is the same data I have on the detail level, but now it's aggregated one level higher. So this is the total, the line total per subcategory, per month, in this case per country. What you can do if you right click on this table, you can manage aggregations. Here I can select my aggregation table. I already preset it up. All these columns you can map them. So this is the category of orders per month. I can map it to product categories category. The country is mapped to country of orders. The date is mapped to the order date. The line total is mapped to the line total. So basically I can map all these columns of the aggregation table to the real columns. And then if you have a report that only is using these columns, then it will automatically use the aggregation table instead of the direct query. So in this case, let's see how that works. So this one is the same report that I showed before. If I choose here 2022, see now it's a lot faster because it's not going to use direct query. It's going to use a DAX query on our aggregation table. But what now if I do a drill through? Do it again. So if you right click here, let's go to the gloves, for example, drill through order details. So now these are details on a product level. This is not an aggregation table. And now if you look, it's using direct query again. So now you basically have the best of both worlds. For the drill through, we use the direct query. And for the dashboard with aggregated data, we use import. Okay, last but not least, we're going to dive into the storage engine. In Power BI, you basically have two engines. The formula engine, that's where the DAX lives. And then we have the storage engine, also called Vertipaq. That's like the database engine. Its official name is X-Velocity In-Memory Analytics Engine. That's a mouthful, but yeah, everybody calls it Vertipaq, which was the code name. It's a column storage, and it has a very good compression ratio. And it's fully in memory. Let's take a look at the column storage. What's that? Normally, if you look like a SQL Server, everything is stored by row. So you have like 8 kilobyte pages, and there all the rows live. So here, for example, I have customers with ID, name, address, city, state, and balance is all in one row. The downside to this is, what if I only want to calculate like the number of cities or per city the number of customers? I need to load all the data in memory while I only need the city and the customer ID maybe. That's why for analytical purposes, they did something else. Column storage means we have a storage only for the columns ID, only the values name, the values address, city, state, and balance due. They're all stored differently, but in the same order, of course. What is the benefit of this? Is that we can get high compression ratios. For example, if you take the quarter column, it's going to order everything based on a quarter, and then we have a lot of the same quarters, the same Q1, the same Q2. So the only thing it needs to store is the starting position and then the number of instances with the same Q1. And then from 311, we have 290 Q2s and so forth. And the same it's going to do for the product ID, for example, but there's some repetition because we have all the products for Q1, we have all the products for Q2, so the count will be less. And some other columns like price, maybe it has too much distinct value, so it's just going to store it uncompressed. But even for these columns, we have a trick to compress it a little bit. This is what I call run length encoding. It's also using dictionary encoding. So if you have a lot of string values, like long text, like city or country, but there also will be lots of times the same values, like Q1 till Q4. It's going to replace it with a dictionary value. So in this case, Q1 is 0 and Q4 is 3. And that's what it's going to store, just the dictionary value. And then if you have whole numbers, for example, you have order IDs that can be really big, it's just going to subtract a big number from it to make the number smaller. This is the orders table. Sometimes you see the ordering can be a little bit funny. For example, it's not ordered by the order ID. In this case, it's ordered by the quantity, and then it's ordered by the product ID. Because you have a lot of the same, that's how it orders. And if you look, for example, with external tools, DAX Studio, if you're going to look into this model, here you can go to Advanced View Metrics, and there you see the size of each table. And if you open up the table, There you can see the quantity is the smallest column. So that's the first thing it's going to order it on. And then it's going to order it on product ID and so forth. And the age, yeah, that's a very expensive column. Why is that? If you look at the data, here we have the age column. It's a calculated column and has a decimal number. So a decimal number is a quite expensive one because it has all these different numbers that it has to save. So what can we learn from this? Some tips. Always look at the compression ratios using Doc Studio to see how big your model is and which columns you might be able to remove or compress them or make them smaller. Always remove columns that you don't need because that will speed up your model. Don't use the date timetables. We covered it before in the other module. Don't use high granularity columns like GUIDs and date times. And you might, for example, split the date and the time, or have like date, hour, minute. Calculate columns can also be a problem. Sometimes they're not being compressed, so it's better to do it in a Power Query or SQL Server. If you follow along with all these tips, you will have a fine, nicely optimized model. With that, we come to the end of this presentation. Hopefully you learned some more about modeling, relational, dimensional, and what's behind the scenes happening in the Vertipaq engine. If you like the code samples, you can download them using this link. And if you have some questions, please feel free to reach out to me via my email or LinkedIn. Have a good day. Thank you.